Hello, this is Bob. This is the second of the four-part series, and specifically this is part one, defining ecological indicators. This whole discussion on how we send flows south from the canal levee system into the downstream natural area, we seem to be at this roadblock. You know, the engineering community wants to know what the ecological indicators are first. How much is the ecosystem telling us we need? And I wanted to look at that in more detail and, throw out there that maybe we don't have to precisely define at this point what that is as a precondition for quantifying how much water we could and should release. So without further ado, moving forward, we need to start with this age-old hydrologic riddle. How many engineers does it take to make an environmental water release? Let you think about that for a moment. It's a trick question. The answer is none. If you first ask a team of biologists how much water the ecosystem needs, the project is indefinitely delayed in scientific inquiry. Meanwhile, the status quo is maintained, i.e., no environmental releases. So how do we answer this question? How much water does the ecosystem need? And to what degree do we need to answer it? If a photo tells 1,000 words, I would argue that the environment needs this much water, as shown in this photograph, for that long. But quantifying exactly how much this much and that long is a difficult endeavor, because the water table, whether it's an area that's purely pristine or an area that's influenced by canals and levees, the water table is constantly moving. It's a moving target, right? So it's not a straightforward answer, because even the natural swamp, an area that's unimpacted by canals and levees, can go naturally dry. But canals and levees, we know, worsen the problem too. And even an area that's over-drained to some degree can get very wet. We were flying over the Big Cypress in an area that's pretty close to a canal that looks absolutely beautiful during peak water season in August. But we know that nearby canal and levee are blocking water and also stealing a water away, so our water does not persist on the landscape as long as it should. Well, fortunately, we have how-to guides and SOPs in the water resources community, and that's how we've gone about establishing our hydrologic monitoring network throughout the Big Cypress and Everglades. We collect water stage in feet above sea level, but then we need to convert water in feet above sea level to an ecological water depth in the swamp in the center of the Cypress Dome. Specifically, we're interested in where the water depth is in the center of these Cypress domes and strands, right there. Because once we define that depth, it allows us to be consistent across the entire swamp. And as we say in Florida, make oranges comparable to oranges, regardless of the elevation differences across the swamp. So for example, Gum Slough may only be 3 feet above sea level, Cowbell Strand 16 feet above sea level, but once we convert everything to depth in the center of the dome, all those systems are comparable. And then it allows us to also to calculate a hydroperiod too, not just a depth, but a seasonal duration of how long from summer, winter, fall to winter, and into the spring, various water depths persist. Now keep in mind, when you're out in the Big Cypress Swamp or the Everglades, everything looks universally flat, but we know it's not. The cypress strands in the Big Cypress are in the lowest spots, and the pinelands are up in the highest spots of the mountains, the Lilliputian Mountains, with the dwarf prairies, the marl prairies, being somewhere in the middle, and less than 3 feet of elevation often separates those communities, the high and the low, and with a water level range of between 0 and 2 feet. So during high water, everything's flooded except for the Pine Islands. And then during low water, the low-lying cypress tend to still hold water, or at least be moist. So here's a look at what those different habitats, that mosaic of habitat in the swamp, looks like on a vertical elevation chart. Up highest are the pinelands, and down lowest are the dry season refugia. And what we define as 0 is the center of the cypress domes. Specifically, that's where the pond apple forests are, or marsh that you find in the center of the dome. So once we know that relative elevation, we can build this simple hydroecological model, which is, I think, worthwhile going through for illustration purposes, to see how the water cycle interacts with the landscape in the Big Cypress. So starting in May, we have the startup of the summer rainy season. And then June, I call it soaking in season, because it takes a full month of June rain for the water levels to fill up the strands and the sloughs, the strands and the domes in the Big Cypress. And then in August, the wet prairies are pretty wet, shallow, ankle deep or so. And then, in September, we might have a big rain day, moves through, and that pops water up into the pinelands, what I call in October peak water. And that's when we also have the peak sheet flow condition occurring in the swamp, with it flowing fastest in the deeper sloughs and strands. And then in November, the dry season starts, water levels drop down. We might have another big rain day in the winter that pops waters up momentarily, but usually by February, water levels are down. And then by March, the Big Cypress, unlike the Everglades, we're perched a little higher. We're more of a drought-vulnerable landscape, and that drought vulnerability can be exacerbated with canals and levees that keep water off of the landscape. April, those wildfires in the absence of water can spread, and then in May, the water cycle starts back up again, and we repeat June soaking in season. So remember, if we go back and look at a photo collage of this, actual photographs of the same cycle, remember we put that staff gauge recalibrated at 0 in the center of the cypress dome. At peak summer conditions, we have about a 2 feet depth in the center of the dome, pond apple forest. And when that happens, the marl prairies might be holding, a foot or so of water, and even the pinelands are shallowly flooded. A pine island that I'm standing on top of looking out. You can see the marl prairie in the background and the cypress domes. And then during the spring drought, typically the center of the domes go dry, or at their max, the maximum drought, we can expect water level to drop 2 feet below the center of the cypress dome, and when that happens, even our deepest flow systems go dry. So what my point in this is we can use all this information. We have monitoring equipment out there, and we define this relationship between the landscape and the hydrology. We can build a better hydrograph that shows just not the water stage, but also the water stage relative to your major vegetation types and relative to the historic record. The dotted line is the median, the 90th percentile. And then all of a sudden, we really get a firm grasp on what the data is showing us. So instead of using feet mean sea level, we look at water depth relative to the center of the dome. We put in the different vegetation types of the Big Cypress mosaic. We can color code those, and then often with a hydrograph, if you tie it into a simple ecological model, this can really help with interpretation too. And again, this ecological model just shows how water levels vary during the spring. Everything can go dry. The water table drops below all the wetland communities, and then during the fall, everything's flooded, and in the summer and the winter, we're kind of in a transition period on either side. So, and then we build this very detailed hydrograph. And I know this is a lot to look at, and I don't want to go into it in detail, but I just wanted to highlight the fact that once we have a history of data going back 20, 25 years, decades, and then we can define that hydrology relative to the ecological vegetation types. And we can see right now, this was in May, where the water level was in May. You can see the entire swamp was dry, and then during the summer, we can expect it to be more resemble this fully flush condition. Once we have that relationship established, then we can do all sorts of things with the data. For example, here it shows the hydroperiod history for Big Cypress National Preserve. The blue bars show the number of days each year, each water year, that the water depth flooded at 1.5 feet deep in the center dome. That's when we have the sheet flow condition occurring, and the long-term average for the preserve is about 4 months. And then we can also define on the lower end the number of days that the water dropped a quarter of a foot below the center of the Cypress Dome. And you can see in the 90s we had a wetter period. We didn't have deep dry downs, but here was when we had the Jarhead fire. Here's when we had the deep fire. It happened when the water table dropped for 4 months below the center of the Cypress Dome. So everything was dry. And then we can use that to develop these ecological targets. So we could say for the Big Cypress and apply it to our area of interest up south of the West Feeder, natural area south of the West Feeder, that our target condition would be the pond apple forest floor in the center of the dome should go dry for less than 3 weeks per year over a 5-year average. Or we could say something like the depth of water in the pond apple forest in the center of the domes should exceed 1.5 feet deep, that sheet flow condition, for 17 weeks of the year over a 5-year average. That's a 4-month period about. And then we can use that data to compare station to station. For example, south of the West Feeder, the best station we have in the Big Cypress is the Cowbell Station, BCA 18, and that's shown in red on this chart. Again, we're looking at water depth, and this shows the 10-year average median water depth as measured at Cowbell Strand relative to the preserve-wide, what I would consider undisturbed average. And you can see what we're seeing is that water levels do not rise as high there, possibly because of an absence of overland flow, than we would typically see in the rest of the preserve, with the result being that we have not achieving that hydro period in the higher elevation wetlands at Cowbell Strand that would be desired. So my point is we can use this data in all sorts of interesting ways to really refine what we want our target condition to be. The problem in our area, and this is the end of this second of the 4-part series, is we have no similar long-term continuous monitoring stations in the natural areas south of the West Feeder. Shown in this photograph is a well that the Seminole tribe, and working with FAU, had the foresight to go in and establish these wells, but they've been discontinued and have a spotty record. So what I would argue is we need 1 or 2 or 3 continuous monitoring stations in that wetland swamp community immediately south of the West Feeder Canal. So in 5 years, 10 years, we're building a robust data set for really pinpointing this question. However, as we move to the second part, the third of the 4-part series, what I argue is we shouldn't let this lack of data impinge upon our ability to go in and define a reasonable environmental release volume and compare that to what is and compare that to how much water is available upstream. So using a back of the envelope calculation. So this is important to define, but I don't think it should limit us going back to the riddle at the age-old riddle at the beginning of the presentation. Thank you for listening to the second part of this 4-part presentation. We'll go on to the third next. Thank you.